Hello everyone and welcome to the 27th lecture of the course Advanced Structural Analysis. We have briefly seen in the previous session the introduction to the computer implementation of the standard stiffness approach, and with the today's session we will try to see that how do we assemble the global stiffness matrix once we have identified the member based contributions in the given system. So, as a concepts which will be covered in this session, we will be looking at the generalization of the stiffness approach which is applicable to the computing environment, and we will identify both the global stiffness as well as the load vectors of the given system. Now, what we have already understood in the previous session, we have said that for a given problem, we identify all the degrees of freedom in the given system, which includes the degrees of freedom which are free as well as the degrees of freedom which are restrained in the given system. And now, as a general idea, we have also come up with a system of the individual members, in which rather than defining the degrees of freedom at only one of the end of the given system, now we have considered all the possibilities of the available deformations of the system, and those we have located at both the ends. So, when we talk about a simple beam cases which are actually non-deformable, we add the two components of the deformations, one the transverse deformation and the second rotation about the normal to the given plane, and those two values are added at both the ends of the given system. So, both the joints which are attributed to the given member I will be contributing these two components of the degrees of freedom at each of the joints, and this way we generate a member based stiffness matrix which is of the size of 4 cross 4. We have also seen that while defining this member stiffness matrix, we include the individual degrees of freedom in the global directions, so that now we have a more generalization of this concept which can be easily applicable to the general degrees of freedom which are available in the overall initial problem or the structural system. Now, as a next step, when we realize that our intention to solve this problem is that we initially constrain all the degrees of freedom, we make a kinematically determinate system in which the system of the loadings will be active based upon the equivalent joint loads of the given problem, and these all loads will be applicable as a conditions of the equilibrium which we will identify for the given system. So, we can consider that whatever loads have been converted as the equivalent joint loads of the given problem, they can easily be identified as the conditions of the equilibrium for the given system, and they can be generalized as the components which we are trying to identify as the equilibrium conditions of the given system. So, any of the load which is applicable in the direction of say degree of freedom 4, that particular amount of force P of 4 will be the one which we will assign to the equation 4 of the given system. And now, the idea is how do we generate the right hand side of the given coefficients. These coefficients, in order to define them, we have earlier also approached the similar problem, and we have identified that one by one we release each of the degree of freedom. Say we release the delta 1, and corresponding to the release of the delta 1 in the given system, we calculate the force in the direction of all of these components P of 1, P of 2, P of 3 up to P of 2n in the given problem. And as we do it, we identify these as the contributing forces with respect to the unit deformation or the amount of delta 1 in the direction of the first degree of freedom of the given system. We can repeat the similar process for all other degrees of freedom in the given problem, and this way we continue for all the degrees of freedom which are 2 of n in the present case, and that is how we have written the generalized expression with all these coefficients in the given system. Now, this remains a very standard approach which we can take up from the structural system point of view, but it has not included anywhere the contributions of the members. So, as if we just realize that this is what we have been discussing, that we define individual degrees of freedom, and each of the members are undergoing some amount of forces at their respective directions of the degrees of freedom of the overall system, and we just write the equilibrium of all these forces to define the net equilibrium conditions of the given system. If we generalize these equations together, we can write them in a very simplified form as the load vector of the given systems is equal to S of S, which contains the stiffness matrix of the overall system, into the amount of deformations which includes both the deformations which are free as well as restraint in the given problem. So, in the defined order of the degrees of freedom, we have identified the overall stiffness matrix for the given system, but this generalization has not taken the member route. We have identified this concept based upon what is already known to us from the simple stiffness point of view. Now, our understanding is, can we do the similar process of or the evaluation of the S of S using the member contributions. So, in this regard we take a simplified problem. We consider a 2 span member in which there are the total 3 number of joints in the given problem. So, we have located the joint 1, the joint 2 and the joint 3 of the given problem, and corresponding to these 3 joints we will have 6 number of degrees of freedom in the given problem, which have been identified as delta 1 to delta 6. Now, this is the condition which is available with the global system. Accordingly, we will also be converting the equivalent joint loads in the given problem. Say these values come out as P1 to P6 in the given problem. So, we realize that we will be writing the equilibrium conditions corresponding to these 6 values of the forces, and the right hand side will be identified in terms of 6 unknown displacement parameters as well as the displacement parameters which are corresponding to the restraint supports of the given problem, and they will all be connected through a stiffness matrix of the overall system. Now, what we will do in order to identify the stiffness matrix of the given system, as we have already said that we one by one release all the degrees of freedom in the given system. So, we will initially release say delta 1, and corresponding to the release of the delta 1 we will define that what is the specific deformation which the system is taking. Once we release this delta 1 value, we realize that at the respective position the forces will be generated. We can call them as now the forces due to the delta 1 contribution in the given system. Now, at the same time what we also realize that the kinematic indeterminacy of the given system, the manner the all degrees of freedom are restrained and only 1 degree of freedom delta 1 is released in the problem, I can easily break this given system into the member components, and the moment I will break it into the member components, the same amount of delta 1 which has been provided at the joint 1 will be released in the member component as well, and I will be considering that the deformation of the given system will undergo in the similar manner. So, the idea of the compatibility will be brought from the overall structural system to the member system, and the similar set of deformations individually in both of the member components individually will also be seen. Now, what it also highlights that as I identify the deformation in the given direction with respect to a value of delta 1, I will also be able to calculate the member forces which are corresponding to the 4 degrees of freedom which are at the ends of the 2 joints of the given member. Similarly, as the second member is also identified which is not undergoing any kind of a deformation, so I will also be able to identify that the member forces corresponding to this system will also be possible to be evaluated, and they are 0 for now in the given condition. Now, this procedure which we have done for any one deformation in the given problem can be repeated for all the subsequent deformations also as per the global system, and what we will also realize that as we define those global deformations in the overall system, individually these cases can also be reflected in the member components. So, what we have seen over here that I identify the first degree of freedom in the given system, the system undergoes the deformation like this, and the same system can also be represented in the member part by identifying the 2 individual members, one undergoing the deformation with the similar kinematic field and the second member undeformed for the given condition, and this is similar to the original idea of the structural component of the given problem. Now, in order to understand now the amount of forces which we were going to calculate in the given system. So, we were looking for the force P1 corresponding to the delta 1 in the given problem, or the force which is corresponding to the moment over here. So, P2 corresponding to the delta 2 in the given problem. I can now realize that these 2 forces in the given system are nothing but P1 of delta 1 is equal to the P corresponding to the member component, the force which I will be getting over here with respect to the member 1, and that is corresponding to the same field which is respective to the delta 1 deformation in the given system. In the similar manner, if I go to calculate the force over here which is P of 3 corresponding to the delta 1 in the given system, I will realize that this force now will be the sum of the forces which will appear at the joint B of the given system in the member 1 as well as joint B of the given system in the member 2 of the given problem. So, I can call it as P of M3 with respect to delta 1, and this one will be called as P of M1 corresponding to delta 1, and this is corresponding to the member 1, whereas this is corresponding to the member 2 of the given system. So, at any given point one can easily identify that the structural components of the forces can be identified in the terms of the contributions from the member field as well. And now, if we look at from the perspective of the stiffness matrix, we realize that as individual these deformations we are providing to the given system. We provide the delta 1 with the given system direction 1, we provide the delta 2 which is the rotation at the joint 1, we provide the delta 3 which is the translation in the joint 2, we provide the rotation, and similarly we also provide the degrees of freedom 5 and 6 in the given problem. What we realize, for all these systems, subsequently I can generate the deformations at the member level, and it reflects the idea that for the set of deformations which are occurring at the respective joints 1 and 2 of the original problem, these deformations are also making the member 1 to undergo the deformation as its standard condition, which we have defined by the form of S of m delta m in the given system. What we mean to say is that all these set of forces which we are generating for the highlighted portion over here are the set of forces which can be easily identified for the member components. For any given member 1, I can identify the corresponding stiffness matrix of the given member and corresponding set of deformations which are available in the given problem, and this can easily be identified for these 4 number of member deformation systems. But we also realize that we have now member 2 also, which is also contributing to the deformation by its own set of 4 similar deformed shapes. So, I can also write the contribution for member 2 by identifying the, so we will just write that P of m corresponding to the member 2, S m 2 which is the stiffness matrix for the member 2, and the delta m corresponding to the member 2 of the given system. Now, what we realize that as the system follows the kinematic conditions, the delta parameters which are defined in the original system, that means the delta 1 value for the problem 1, or delta 2 with the problem 2, or delta 3 or delta 4 subsequently in the given system, they are reflected in the same magnitude in the structural system or the member system as well. So, when I go with the parameters of evaluation of the delta for the member component, I realize that the delta for the member 1 is having the same set of values which are identified with respect to the 2 ends of the given problem, and we can locate them with the values of delta 1 to delta 4. Similarly, when I go with the delta parameters for the member 2, I realize that these are the values corresponding to the node 2 and 3 of the given problem, and node 2 and 3 are undergoing the delta deformations which are identified as delta of 3, delta of 4, delta 5 and delta 6 of the given system. So, corresponding to these 4 cases, we get the contributions of the member 2. Corresponding to these 4 cases, we get the contribution of the member 1, and this way we understand that now if we want to assemble the overall stiffness matrix of the given system, we can easily do it by adding the contributions of the individual member based stiffness coefficients of the given system. Now, the idea of the stiffness matrix which we have identified over here is a 4 cross 4 stiffness matrix, which is of the size for the 4 degrees of freedom identified for the given members and its 2 ends of the degrees of freedom. Similarly, the stiffness matrix for the member 2 also appears in the same manner, a 4 cross 4 stiffness system. The global stiffness matrix which we are looking to evaluate, the S of S, is attributed to 6 degrees of freedom in the given system. So, I can call it that the original size of the S of S which is expected to be evaluated is 6 cross 6 in the given problem. Now, with this idea in mind, I realize that if we just extend the S of m having a standard size of 4 cross 4, which is corresponding to the individual degrees of freedom 1, 2, 3, 4 in the given problem, I consider that the S of m can be highlighted in the same manner as it was evaluated earlier, and it has been attributed to the degrees of freedom which are corresponding to 1, 2, 3 and 4 of the given problem, as we have understood that these are the 4 cases of the deformation which are contributed by the member 1, and this is the contribution which I am looking for, and the remaining all the other parameters of the global stiffness matrix will be 0 for this given case. So, this is a standard idea which can be reflected by considering that member 1 is contributing to the overall stiffness of the given system, and out of the 6 cross 6 stiffness matrix size which we are trying to evaluate for the S of S, the 4 cross 4 stiffness contribution is appearing in the degrees of freedom directions 1, 2, 3, 4 with respect to the member 1. In the same manner, now we look at the SM2 which is the member 2 contribution, and we understood that SM2 is contributing corresponding to the member 2, and member 2 is attributing to the degrees of freedom 3, 4, 5 and 6 in the given problem, which means that now out of the similar context of the stiffness contribution, if we make it over here, we identify the degrees of freedom 1, 2, 3, 4, 5 and 6, and out of that now we realize that the member 2 contributions are with respect to the degree of freedom 3, 4, 5, 6 in the given problem. So, I will consider now that corresponding to the rows 3, 4, 5, 6 and column 3, 4, 5, 6, I have the SM2 identified in the given problem. So, the 4 cross 4 matrix which is corresponding to the member 2 in the global directions has been fitted to this particular position, and all the remaining parameters of the given system or the given matrix will be identified with the 0 values in the given problem. And now, once we are able to make this kind of a generalization, I can add the contribution of the SM1 and SM2, and I can say that this will be the effective stiffness matrix which we are trying to identify for the given problem. Now, this same realization we also bring it from here, that the sum of the forces which we are doing in the given problem at any particular point, when we look at into the structural form, this is the force which is defined at the position 1, and this force is identified in terms of the value of the force which is in the member 1. Similarly, when we look at the force 2 which is corresponding to the degree of freedom 2 in the given system, we also look for the member force in the member 1 corresponding to the second degree of freedom of the given system. But when we go to the force number 3 in the structural system, we realize that this is the sum of the force corresponding to the member 1 as well as the force corresponding to the member 2 of the given system, and taking the sum of these two, it gives me the net resultant force which is active in the direction of P3 in the global system. And by doing this kind of a sum, now we realize that we have a contribution of the stiffness matrices which are defined at the member level, and as we already know them in a very generalized manner, now rather than calculating the stiffness matrix for the structural system in an entirely new way, I can just assemble the stiffness matrix by adding the contributions of the member parts. So, I just write the contributions with respect to all these force components which are the corresponding forces for the member 1, corresponding forces for the member 2, and all of these are the coefficients of the stiffness matrix which we have already defined in the member coordinates. And now, as per the condition of the equilibrium, we just write the force conditions for the P1, P2, P3, P4 and P5 to P6 in the given problem, and we realize that these forces can be added together in this very simplified manner. And if we look at the overall expression by taking that the common coefficients, like when we look at the degree of freedom delta 1 with respect to 1, we realize that this degree of freedom should be same as the original delta 1 which is available in the given problem. Similarly, delta 2 corresponding to the member 1 is same as the delta 2 of the original system or the structural system. Delta 1 corresponding to delta 3 corresponding to the member 1 is same as the delta 3 of the original system, and similarly delta 4 of the member 1 is same as the corresponding degree of freedom 4 of the global system. In the same manner, when we go to the member 2, we realize that delta 1 for the member 2 is the degree of freedom which is appearing over here, and that is delta of 3 in the given problem. Similarly, delta 2 corresponding to the member 2 is the delta of 4 in the given problem, which is the rotation over here. Similarly, delta 3 corresponding to the member 2 is delta of 5, which is the translation at the third joint of the given problem, and the final value is the delta 6, which is the rotation at the last or the end joint of the given problem. So, keeping these ideas in mind, we can easily assemble this equation in terms of the equivalent set of forces which have been identified and the corresponding values of the deformations which are located for the structural system. So, whatever we have now inside defined for these stiffness contributions have all been brought from the member stiffness contribution. So, we realize that now easily one can contribute the stiffness contributions of the given system with respect to the member 1 or member 2, because we were solving a 2 member system for now, and this is attributed with the 4 cross 4 stiffness system which is identified over here. The 2 rows and 2 columns of the given system will be getting contributions from both the member 1 as well as member 2, and we will be doing the sum of the coefficients of the matrix for those positions of the given stiffness coefficient. With this idea in mind, we understand that the global stiffness matrix can be easily assembled with respect to the overall contributions of the stiffness contribution of the individual members. Now, we can generalize the same idea for a larger system. If we have a system having multiple degrees of freedom and the multiple spans in the given problem, as per the system, say we have n number of nodes in the given problem. So, starting with the node 1, node 2 and up to the node n, we have total 2n degrees of freedom in the given problem. Now, corresponding to any particular deformation which we provide to the individual degree of freedom, we realize that individual members can again be broken into the similar manner, and they will also be defining the contributions of their own corresponding to the given system. So, when we apply the delta 1, we realize that the contributions will only come to the member 1 and remaining all of the members will not be contributing anything to the stiffness parameters. And we also understand now that in the global system corresponding to the 4 degrees of freedom which are identified at the 2 end joints of the member 1, these 4 degrees of freedom will always be getting the contributions from the member 1. So, now if we are going to assemble the stiffness matrix for this given system, which is of the size 2n cross 2n, because there are 2n degrees of freedom, we understand that the 4 cross 4 stiffness matrix of the given member 1 is going to sit in the place of the first 4 degrees of freedom of the given system, which are identified in the given problem. And this way we can now keep on identifying the place of individual members and the contributions of their degrees of freedom in the overall process. If you look at this process in the similar manner for any generalized case, we have a degree of freedom which is corresponding to the degree of freedom I in the given system. We provide it as a rotation. Corresponding to that, the contributions will be provided by both the members which are on the left and the right of the given system. So, now when we are adding the contributions corresponding to this particular degree of freedom, we realize that the contributions will be attributed by both the member which is on the left hand side of the given system as well as the member which is right hand side of the given problem. To generalize these concepts, now we can simply say that in a given system which is having the 2n degrees of freedom in the given problem, any ith member which is identified with the 2 ends of the given problem, say j and k, corresponding to the nomenclature which we have already done, we can identify that the given system will locate the 2 degree of freedom in the given problem. So, if I locate as per the present idea that this is the degree of freedom 2j minus 1 and this is the degree of freedom 2j in the given problem. Similarly, at the joint k we have 2 degrees of freedom, this is the 2k minus 1 and this is the 2k in the given system. So, we realize now that the contribution of the stiffness which is going to appear for the SMI, the ith member of the given system, is going to sit at the position of the degrees of freedom 2j minus 1, 2j, 2k minus 1 and 2k in the global system. So, I can bring the rows and columns corresponding to the 4 values which are assigned with respect to these degrees of freedom, and I can say that the contribution of the SMI will actually be provided to that position, because those are the positions which are contributing to the deformation of the member I in the given problem. So, if we provide any kind of global deformation in the position of these degrees of freedom, the deformation will also be adopted by the given member I, and that is where it is going to contribute to the overall stiffness of the given system. So, with this idea in mind, we have identified a structured approach to define the global stiffness matrix. The contribution of each of the member can be mapped with respect to the respective degrees of freedom in the global system, and once we have identified it, we can keep on placing these individual member stiffnesses in the given system. Once we are able to do it, we also realize that corresponding to the same contributions of the degrees of freedom which each member is scattering, we can also assemble their contributions of the respective member forces, and this is what we will try to see in the next session. With this, we stop over here. Thank you everyone.